Okay, so today we're talking about blockchain and Bitcoin. It's not really a security issue. It's sort of an application, but it's pretty interesting and it builds on a lot of things that we've seen. So what I want to do is sort of talk about what is the vision of digital cash? What is it? What is digital cash different from sort of a digital payment system like using a credit card? How is it sort of done in the past? And then what is new about Bitcoin and how it works. And if we have time, we'll talk a bit about Ethereum, which extends Bitcoin with this idea of having what are called smart contracts, where you can actually sort of execute little pieces of code automatically in response to a transaction. So this whole idea kind of started off in the 80s. There's this guy named David Chaum, and he was sort of somewhat of a libertarian and had this idea that we should build a new electronic payment system. That it should be sort of through computers and through encryption, it should be very easy to build a secure payment system that didn't need to rely on banks and governments and things like this, and would have the property of anonymity. So the nice thing about cash is when you pay for something, nobody knows who you are. There's no record of who you are. And so for people who value their privacy, this is an attractive property. If you use a credit card for everything, there is a record of where you were when you bought it, who you bought it from, and who you are. And so David Chaum's vision was some sort of electronic payment system that did not sort of cause you to lose your privacy when you pay for things. The challenge, though, is that the privacy that you get sort of causes some problems. So one of the biggest problems that existed back then and still happens today is in an anonymous system, if there's fraud or something goes wrong, how do you get your money back? Nobody knows who you are. It's somewhat hard to sort of prove when you spend cash. It's hard to prove you spent cash because it's anonymous. There's no record of it. So complaining about a transaction and trying to get it voided is very hard. And this is sort of the trade-off to some extent of having sort of a digital payment protocol that doesn't record who you are because it's very hard to sort of undo things later. So if we look at digital payments, there's sort of the way that most companies do it today is sort of through credit cards. So vendors like, we pick Amazon because it's big, they might establish an account with some payment processor like PayPal. So PayPal's job then is to sort of get credit card numbers from Amazon when people want to buy things. They will then sort of take care of contacting Visa or MasterCard and ultimately the bank that issued the credit card. So for example, my cards are from UW Credit Union and Citibank. So whenever you buy something, the person you're selling it from will contact PayPal, who contacts your bank to make sure it's a valid credit card, not expired, whatever the rules are. And the bank will then authorize a transaction, saying, okay, go ahead, buy something. The seller can then record the transaction, and at some point later, it'll send a settlement message saying, okay, here's the transactions I made during the day. Please move all this money to my account. So the key is that this is an online protocol. When you're buying something, there is a message that goes to your bank saying, you want to pay this money now from this account to the seller account. Or at least there's an authorization for that. And so it means that to some extent, this can be difficult to scale, to have lots and lots of systems. So when people came out with digital cash, people thought it would be impossible to do sort of internet scale credit card processing. It turns out we have it today, so clearly it's possible, but it's a lot of very expensive to build. It takes a lot of money to sort of build and maintain this big payment processing system. And it means if you want to launch a new credit card or a new payment system, it's very hard to build something on the scale of what Visa and MasterCard do. So the other property of this is that there's no anonymity because you have an account that records your purchases. This is nice so you can see when you're spending your money. But for example, I have a problem that I share an account with my wife, and when I want to buy her birthday presents, they all show up in my bank statement that she can see. So she can see in advance, like when I go to a jewelry store, she can say, as she has, oh, I saw you bought something at the jewelry store. Was that for me? So anonymity sort of bites me in that kind of case. So that is sort of one of the goals. So people have proposed digital cash. And the idea with the digital cash is we want the properties of cash, which are untraceable digital money transfers. And we want to do this all, though, using encryption, and we would like to sort of make it as safe and secure as sort of the credit card-based mechanism. So the basic way people propose doing this is that a bank issues what we're going to call digital coins. These are essentially digital certificates the bank signs that say this certificate is worth a certain amount of money. The bank will then sign these over to some user, and a user can then transfer them directly to some other user or seller. That seller then can go to the bank and verify that this money is correct and convert it back into sort of regular money. So we're going to have sort of a person-to-person protocol based on encryption that says how we're transferring money around. So let's look at a quick example. We're going to use the bank of Goofy. Goofy's going to create some new coins. And to create a coin, we have to make sure that it's a valid coin that comes from Goofy, right? We don't want people to make money. That is an important part of a cash system, is that not everybody can just fabricate money. Even though it's just a sequence of bits, it has to be the right bits. If everybody can make money, that is not cash, that is just garbage. So the way we're going to do this is we're going to create a coin with some unique ID, and this unique ID lets Goofy track how much money was handed out, how much this coin is worth, and it's going to be signed by the public key of Goofy. The coin itself is going to have sort of something encrypted with Goofy's secret key. Okay, so I take it back. The certificate is signed by the secret key of Goofy. So when Goofy issues a coin, Goofy will sign it, which is Goofy's secret key. Only Goofy can do this. That's how Goofy can tell it's a legitimate coin. When Goofy wants to give it away, Goofy can add a note to it that says, I want to give this coin to Alice, and he can identify Alice by her public key, and he can include a hash over the coin. So the idea is that we are going to have a statement that is signed by the secret key of Goofy, saying that it's going to pay to a public key. I apologize, this says secret key here, I didn't quite fix it. And it's going to have a hash over the coin. So we can identify exactly which coin is being transferred. We can say which key we are paying it to. Now notice we're not saying which human, we're just saying which key. So the difference between keys and humans, which normal banks don't maintain, they know for every account number who the human is, that is sort of what provides anonymity here. So this means that Alice can take this combination of the coin from the initial coin signed by Goofy and the transaction that says it was transferred to Alice. This means that Alice now owns the coin, and Alice can potentially either give this coin to someone else, or Alice can take it to a bank and transfer it back to US dollars or euros or renminbi or something like that. So in this case, Alice can pass it off to Bob, doing the same thing, adding another transaction that says, I'm going to take my coin and I'm going to create a hash over this coin, and I'm going to include in this a statement that it's now Bob's coin. And Bob can now take this, this certificate and present it to someone and say, look, through this chain of signed information, you can believe that I have this coin and you should accept it as payment. So far, so good. Do you see any problems with it? Yes? Okay, so one problem is this chain, as you pass coins around, there's studies that show that, a dollar bill goes through like 300 people a year or something like that. So this chain gets longer and longer as more people spend it. So do you have a thought on how we might solve that? Any ideas? Who is in a position to reduce the length of the chain? So the entity that's in a position to break the length of a chain is the entity that can sort of create a new coin that doesn't have this long chain of things on it. So the way you might simplify this is to say, what if Bob takes this coin and pays it to Goofy and says, here Goofy, here's a coin, and in return I want you to give me a new coin with no chain on it. And so at any time, anybody who has a long chain that gives them a coin like this, they can take it to a bank, effectively a digital bank, and say, please make change for me by sort of getting rid of all this cruft and just give me the shorter version, give me a new coin, that is transferred directly from the bank to me without this whole long list of certificates on it. So that's how we can shorten it at any time, by going back to some central authority that can sort of verify the whole chain and then remove it all and issue new coins. Other problems with this? Yes, over there actually. You are just talking. Your thoughts. All right, so another problem is that Alice might try to spend the same money twice. Right? She might try to pay it to Chuck also. She still has, you know, when you spend digital money, you don't have to delete your copy of the certificate. You still have it sitting around. You can just sort of do the same exact process, but sign it over to someone else, in this case, to Chuck. So now there's a question, which is Alice has given this money both to Bob and to Chuck. What actually happens? And this is called a double spending attack. Did you have another thought? No. Okay. So it turns out this is the central question for digital cash and money transfers. How do you prevent double spending? So how do we do this in this world? In sort of this world that I presented to you, how could you prevent double spending? Yes.
You keep the money and you don't have money.
So how do you make sure that you don't have money anymore when you transfer to someone else? Well, so we haven't said anything about balances or accounts here. All we've said is think more like coins. This is a certificate that says these set of bits right here, we're saying is worth $10. Just possession of these bits. Signed over to Alice and knowing Alice's public secret key is enough to spend the money. There's no account anywhere that says how much money Alice has that we need here. Because having that account would mean we don't have privacy, because we can then see the transactions against that account of who's spending money to some extent. Your hand up?
So you can just keep a very global ledger that keeps track of everything. And when you pay somebody, it's signed on the ledger. So
okay. So what you're getting at is what Bitcoin does. So one way we can do this is we can have a global ledger that has every single transaction in the world on it. And we can, whenever we make a transfer, we can write this down on this global ledger, some big list of all transactions. And then I think you're suggesting when somebody gives us money, we can go through this big long list and say, is this money actually belong to the person who's giving it to us, or did they already spend it? And we can detect the difference by looking at every transaction so far. If the money has never been spent, then we believe it's valid. If it's been spent before, this is a bad transaction, we reject it. So we'll talk a lot about that for about 50 minutes or so. In the absence of the problem with that is it's a big complicated thing to have a global ledger, and there's a lot of details of how you get it right. Is there something simpler we can do in the Bank of Goofy? Yes?
Can we just update the unique coin ID every time we make a transaction?
So we could. So I think what you're suggesting is when Bob receives this money, Bob could immediately go to Goofy and say, here is some money that Alice gave me. Can you take this money away and then give me coins with a new ID that are given directly to Bob? And then Goofy can remember that this unique coin ID was already spent and consumed. And when Chuck goes to Goofy and says, you know, can you take this money from Alice and transfer it? Goofy can say, oh wait, this money was already given away. I can't give it back to you. So it's the same exact principle. The difference is instead of having a global ledger everybody can see of all transactions, we are going to keep that ledger at a bank, the Bank of Goofy, and every time you spend money, if you're worried about double spending, you have to go to the Bank of Goofy and make sure the money wasn't double spent. So this approach of having this central entity that you trust, that verifies things, was sort of how digital cash worked in the 80s and 90s. That there could be lots of banks, they'd issue cash, you could spend it. You had to go to the bank to sort of make sure that it was valid coins when you got it. And so the challenge with this is that it doesn't necessarily scale. You also have a problem that the bank could be misrun. It could sort of, there's nothing that stops a bank from issuing a lot more coins than they actually have. Right? I could start a bank and I could start issuing digital coins worth $10 each to everybody in the room, even though I don't have all the money. And when you came and tried to cash it in, you'd be out of luck because there's no money behind it. So it's sort of, you're relying on the bank to sort of properly only give out coins for the money they really have in the system. So this idea, it was a nice idea. It didn't really go anywhere. So part of the problem was this trusting banks. It turns out people actually trust their banks. Banks are heavily regulated. They don't actually, except the exception of 2007, they usually don't hand out a lot more money than they have. It's happened. The big challenge with this is that regulators said, we really don't like having anonymous payments. We don't want you, hiring hitmen with anonymous money. We don't want you buying drugs with anonymous money. We want money to be, or paying terrorists, we want it to be traceable. And so if there's any central entity like a bank involved, we will have laws that prevent banks from supporting this. So that centralized entity of a bank is a point where the governments get involved and shut it down. So this model of having a bank issuing digital cash didn't really go anywhere. So this other guy, Nick Szabo, had the idea, and his idea was to say, he sort of looked at, where does money come from? Money comes from governments printing money. Why does it have value? We believe the government is not going to print too much money and cause inflation and overvalue it. If the government does the wrong thing, our money is worth very little. So certainly in countries like Venezuela, the amount that money is worth cuts in half every week or something like that. So he was really interested in what do you do as a basis for money that is not sort of controlled by government bureaucrats, but is sort of a natural basis for money, more like gold. And his idea is to sort of say, what we will use as a basis for money is really computational power. That we will sort of say, we will use the ability to do lots and lots of processing as a way to sort of validate that something has money, and we'll find a way to sort of do something digital, very distributed with no centralized entity. And the key is going to be this notion of a pure proof of work, which is going to be to sort of make a system work, we are going to do a huge amount of computation. And one thing this is nice is that if you have to do a lot of computation, then we can distribute that across the whole world. It's hard for any one person to do enough computation to take over the system. In the case of the bank was doing all the validation. So one person at the bank could undo that whole banking scheme. If we are saying we are going to do distributed computation across the globe, then hopefully no one person on Earth controls enough computation to sort of invalidate the system. So that leads up to Satoshi Nakamoto, who still remains unknown. And in 2008, he posted on this Anon mailing list saying, I've developed a new open source peer-to-peer digital money system. You should take a look. It's decentralized. There's no centralized servers, meaning nothing to take it down. And it's based on sort of cryptographic proofs of work instead of having some central source validate things. So one of the key things about this is trust. So in a normal system, like when I give you a check to pay for something, there's a lot of trust involved. You have to trust that the check I give you is actually a real check. You have to trust when you take it to a bank that the bank will accept the check and give you money for it. You have to trust that the money you're getting back in terms of green bills will actually be worth something. So he wanted to build a system where where the trust is all sort of cryptographic trust. You're trusting that RSA works or that SHA-256 works. You're not trusting that humans are doing the right things. And he sort of compares this to say, if we think back to sort of early in the semester, we talked about how operating system protects users from each other. They have access control lists. There's an administrator who sets those access control lists. What this means is that if I want my data to be secure from you, I have to trust the administrator will properly enforce access control lists so you cannot access my files. In contrast, using cryptography lets me encrypt my files with a key that I control, and no matter what the administrator does, the administrator cannot give you access to my file contents if I do this correctly. And this is the difference that he's proposing in money today, where you have to trust central authorities to do transfers and things, versus a truly decentralized system where you're just trusting that cryptography works. So the goals for this system is an electronic payment system that guarantees the safety of transactions so they actually get executed properly and everybody agrees that the money was transferred. It protects against double spending, but it gives full freedom to owners in terms of who they want to pay and how much they want to pay. There's no central trusted authority, and we're not going to rely on some quorum, which is the idea of if we have enough computers agreeing, we're just going to trust having enough computers. We're going to have something that is stronger than just saying if you have 3 out of 5 people, majority rules, saying we're going to accept a transaction. And the way we're going to do that is with this notion of a proof of work, which we'll go into. Any questions so far? Okay, so we're going to start off with sort of an example of what we want to have happen and how it works, and then we'll sort of go deeper and deeper into the layers of Bitcoin to explain how it works under the covers. So suppose we have a set of nodes. We're going to assume that we want a distributed system where there's a bunch of nodes out there on the internet talking to each other, and these nodes are going to be the entities that sort of keep track of who has how much money. They will be sort of a distributed bank that says how much money each account has. And to these nodes, you can submit a transaction. For example, Alice is going to pay Bob for transaction 1. Alice is going to pay Carol for transaction 2. The job of these nodes is then to look at these transactions and sort of figure out the real truth. What actually happened among all the competing transactions? So in this world, we might have different nodes that all see different transactions happening. So node 1 sees transaction 1, node 6 sees transaction 2. Because it's a big, gross, disgusting distributed system, they're not all going to see the same thing at the same time. If you ever take CS 739, you can spend 4.5 months learning why this is hard. And it truly is interesting. And so the key is, how do we sort of know when there's a new transaction, which of these 2 transactions is the real thing? There's some evildoer out there who wants to submit fake transactions, perhaps, double spending money, versus good transactions that are doing the right things, and we need to distinguish the difference. So how are we going to do this? And this is sort of the genius of Bitcoin. The idea is that to validate a transaction, you have to do a lot of computational work. You have to do, roughly, say, a quadrillion computations to accept the transaction. So that's a lot of computations, and what it means is that any one node can't do a quadrillion computations on its own. Instead, what we're going to do is we're going to distribute this computation across all 6 nodes of the network. They're all going to work on different parts of it, or maybe overlapping parts. They're all going to try to do this computation, and it's going to be a puzzle. They're all trying to solve a puzzle. So then, ultimately, hopefully, the goal for Bitcoin is within 10 minutes, somebody will find an answer to the puzzle. And whoever finds the answer to the puzzle first says, yay, I found the answer to the puzzle. And the idea is that whoever answers the puzzle first, this transaction wins. So in this case, the node 4, which was looking at transaction 2, found an answer to the puzzle first. And so everybody should agree that transaction 2 is the right transaction. And so everybody else will sort of agree that transaction 2 comes up. So far, so good? Okay. However, it is possible some other node will find a different answer to the puzzle. These are not going to be unique puzzles. So node 1 might say, wait, I found an answer to the puzzle also. You should listen to me instead. So we have multiple answers to the puzzle. And so the second piece that Bitcoin has is it says that in the existence of multiple people who have sort of different views of the set of transactions out there, valid nodes will always accept the longer sequence of transactions. The thing to remember is that each valid transaction here took a whole lot of work, like a quadrillion things. And so this means that if the valid nodes already went to TX2, we're going to have more people trying to solve the puzzles for TX2. And so we can make this chain get longer faster by solving more puzzles. If people don't believe TX1, fewer people work on it, that chain will grow more slowly. And very rapidly, the chain starting at N4 will get very, very long, and everybody will agree on it. The chain from N1 will sort of stay short because nobody believes it. And so this is sort of the self-correcting mechanism that Bitcoin has that will allow you to sort of, when something goes wrong, it allows us to sort of self-correct and automatically choose sort of the good path of the correct transaction. Yes? So there are no guarantees. It's really just heuristics. It doesn't guarantee it. You could get very unlucky. Somebody could solve a sequence of puzzles very quickly, and it just counts on the fact that it's highly unlikely people will do that. So Bitcoin is not, in the sense, Bitcoin is not sort of absolutely correct, but it is sort of cryptographically difficult to break, and it's difficult to not, it sort of works well enough in practice that people will invest billions of dollars in it. Yes?
Is it possible that some transaction is not accepted by the network at all?
It is possible that it's, I mean, if the transaction, I believe, if a transaction is invalid because somebody's trying to double spend, then it will be rejected. If it's a valid transaction, it should eventually be accepted. Because there's a problem. You may have proposed transaction TX1 and ended up on this losing side. And so what it means is you now have to resubmit transaction 1 to try to get it onto the winning side. So if you keep doing that, eventually it should work. But there's no strong guarantee that you necessarily will work. It just, again, works out in practice. Okay. So the next thing we have to do is sort of figure out how do we build this chain of transactions that everybody agrees on. And the way we're going to do that is with this concept of a hash pointer. And the idea here is we can think of a hash function over some data. Really, it's a pointer to that data because it uniquely identifies that data. If the data changes, then the hash is not valid. But you can sort of verify the association between a hash and some data. Once we have that, we can build a chain, right? So we can have a hash of some data that incorporates a hash of previous chunk of data that incorporates a hash of previous chunk of data. And this creates effectively a tamper-evident log. What that means is that if any of the data changes, so if, say, a block in data 1, some piece of data, byte of data in data 1 changes, that will change the hash of the previous block, which will have a different hash, which makes the hash of the previous block in the node on the right become incorrect. So this allows us to verify that all the data chunks of this big, long chain, as long as we want to make this linked list, are all correct. And it lets us build it incrementally, right? We don't have to hash all the data at once. We can hash the data now and then keep on adding on to it. So this is called a hash chain. Make sense? And this is just simple hash functions like SHA-256, no keys involved yet. So this is really what a blockchain is. A blockchain is an append-only hash chain where the data items here are going to be a transaction or perhaps a set of transactions to make things more efficient. And what this does is this gives us an ordering of all the transactions that are executed, because they will all the ones executed will show up at some point in this chain, and there's an ordering that transaction 5 came before 6, came before 7. So for example, if Alice is double spending and she spent money first through transaction 5, we can walk through this chain and see that she spent it and reject the transaction to send the same money to Chuck. If she hasn't spent it, then we can append a new transaction saying exchange that money to Chuck. So this is indeed, as you suggested, going to be the global ledger of all transactions, and this is how we keep making it longer, and we can keep verifying that it's correct. So the reason this works, as we talked about before, is that reversing a hash or finding a hash collision is very difficult. So we want a nice hash function, so you can't replace transactions with some other transactions and still have all the hashes work. The other thing we might want to do is verify that a single transaction, if somebody says, here's a transaction, is it actually part of the blockchain? We might want to verify that, and it can be difficult to verify because you might have to rebuild the whole chain. So the other cryptographic tool we're going to use is called a Merkle tree, and it really is it's a binary tree where each node has the hashes of the two children. So as we can see here, for example, on the left, we have two data items. The next node up has hashes of the two of those. The node above that has hashes over its two children. So that hash on the left at the second level from the top incorporates data from all 4 blocks. So this means that if any one of these 4 data blocks here changes, then the parent block will change, which means the grandparent block will change, and the change at the root, the thing at the root will change. The reason this is nice is that it's very efficient, because I can verify that a piece of data is correct by just verifying the hash chain above it. I can say this data is hashed correctly, that the node above it is hashed correctly, the node above that is hashed correctly. So that means I trust that this transaction, which is in the data, is actually accepted into the blockchain. So this is a way that if I give you some money, you can sort of test, is the money you're giving me correct according to the blockchain, because the transaction that gave you the money is part of the blockchain. So this is how we will sort of let you verify money can be transferred. Any questions on this? Yes?
Where is the structure maintained? And is it in every node or shared?
So the structure, the blockchain itself is maintained in all those nodes of the distributed system. So there's some set of nodes that make up Bitcoin, and they all have a complete, they more or less logically have a complete copy of the log. They're all maintaining a complete copy of the log of all transactions that ever happen. And so you can go to one of those nodes that are part of Bitcoin and ask it to either verify that a coin is correct, or you can ask it to accept a new transaction. And then it will try to extend the blockchain. So this is sort of exactly what you're asking. So the blockchain is this shared ledger. A transaction is authenticated because we're going to sign it with the secret key of whoever has the coin currently. And we're going to do a transfer to somebody else, which is going to be encrypted or indicated by their public key. So this will sort of authenticate the transaction so that you're sort of you can only give away your own money because you only know your own secret key, and you can identify who you're giving it to through their public key. This also makes it unforgeable. Another unique thing is it's decentralized. There is no central bank. Instead, we have this distributed system which maintains a copy of the ledger. And it's really getting that distributed system to agree on the contents of the ledger, which is the job of Bitcoin or the blockchain. It's consensus-based. There's sort of a single copy of the whole ledger for the entire world, which causes some problems. There might be branches for a short time, as I mentioned, if there's two sort of people who sort of do the solve the puzzle, find a solution, but those sort of branches very rapidly die off because they don't get enough people trying to extend them. So in general, this is a valid technique for sort of keeping track of any kind of global distributed information. So IBM is pushing this as a way to do supply chain management. If you want to sort of agree on, you know, I ship something to you and you ship it on to him, we might want to agree on where an item is, and we can use a blockchain to sort of agree globally on where this item is in transit without having to have some single server somewhere that you trust the operator of that server to do things correctly. Okay, so in Bitcoin, if you're going to pay somebody, you have to have an identity to which you pay or some address to which you pay. This is your Bitcoin address. It is really a public key, private key pair. Your public key is hashed and published as your address. And so when you do a transfer, you don't actually have to encrypt it with the public key who's receiving it. You just have to include the hash of that public key in the transfer. The transfer is public, but it means that anybody, to sort of accept the transfer, you have to prove you have the secret key that corresponds to that public key. So if you want to receive money, you can publish your address, people can then pay you. So in that WannaCry example, there was a Bitcoin address to which you're supposed to pay $300 to get your data decrypted. So one thing to note is there is no certificate authority that binds your address or your public key to your identity the way that we saw with TLS. Why not? Why don't we need certificate authorities here?
Keep it anonymous.
What?
Keep everything anonymous.
Right, so it certainly keeps things anonymous. Right, because of certificate authority, the whole point is to sort of attach a real-world identity to a key. And here we don't want a real-world identity. We want to be able to like sell our drugs anonymously. Or perhaps submit, you know, we could use this for course evaluations where you submit them with Bitcoin. Maybe blockchain, not Bitcoin. So to some extent, you're right. Part of it is a desire to be anonymous, but it also says we're not going to solve the problem of how you get your identity to someone else correctly. That is your problem. Like if I want to get money from you, I have to give you my public key, correct? So the problem is he has an incentive when I give you my public key to sneak his public key in instead. you can't tell the difference, and if you pay me, you'd actually give money to him. And so Bitcoin does not solve this problem. It sort of says this is somebody else's problem. You can use TLS or anything else to solve the problem of how you securely communicate public keys. So if you want to use certificates for that, you can. We're not going to require it. It's up to you to make sure you're sending it to the right place. Okay, so to receive money, what the payer has to do is generate a transaction. And in the transaction, it's going to be a record that is going to be added to the blockchain. And it has the existing Bitcoin you're using to spend. The amount has some metadata info. It has your block address. And it's all going to be hashed of the previous transaction that spent this coin. So the idea is we are going to link this spending of the coin against the previous spending. This is the same thing we saw with the Bank of Goofy, where Bob extended the coin that Alice gave him to pay to someone else. So we're going to have this chain of transactions that are global, all transactions in the world. There's also a chain for the spending of every Bitcoin out there. Every individual transaction is all going to be linked together as well. And this is all signed with the secret key. And the idea is the secret, we can, anybody who can find the public key can sort of verify that signature is correct. So this is sort of what the chain of transactions for a single Bitcoin record looks like. There's a, the original owner, public key is incorporated in the hash, and it has the signature over this coin from the original owner, owner 0. When this is transferred, there's going to be a transaction that owner 1 creates that includes owner 2 public key, a hash over the previous transaction, and it's going to have a signature from owner 1, etc. So this gives you a chain for every transfer, all the people that it goes through. And what it means is you can start at the end and you can verify this back to some original primordial world where Bitcoins are created by just walking through this chain and verifying all the keys and hashes are correct. So again, we are trusting cryptography here. We're not trusting humans at all. So this is sort of what an actual transaction looks like. It's got our hashes, it's got metadata, it's got the previous hash, it's got a signature over the sort of original coin. It has the value of how much Bitcoin are being sent, and it has the public key of who it's being sent to. So this is sort of a PayCoin transaction, and you can actually use this to pay multiple amount with multiple coins at the same time. If I want to pay you, say, 5 Bitcoins, and he gave me 3 Bitcoins, and you gave me 1, and you gave me a half, and you gave me 1.5, I can do a transaction that says, take all these Bitcoins that I have and transfer them all to you. And so I can pass in a bunch of different Bitcoins, and I can have a number of different recipients who are receiving different amounts all at the same time. So one thing I can do, for example, is suppose I have a Bitcoin that's worth 10, and I want to pay you 5. I can do a transaction where I pass in 10, and the outcome is that you get 5 Bitcoins and I get 5 Bitcoins. So this is a way that we can sort of break a Bitcoin up into smaller pieces and make change by just having a transaction that merges Bitcoins together, or that takes a Bitcoin and splits it up into smaller pieces. So this would be the transaction that goes into the global blockchain. So it means that we don't necessarily have sort of a simple linear linked list, but we actually have a graph where Bitcoin are sort of merging and splitting as they go through multiple owners. So far, so good? I see a lot of blank stares. Some smiles. Okay, so I haven't said where coins come from. So there's a separate transaction type which creates a coin. So you can create a coin under certain circumstances and say who the recipient is. And so this is just another transaction type. The trick is, how do you get everybody to agree that this transaction is a valid transaction? Because you have to get consensus among the entire blue block of nodes that you have a valid transaction. So for example, if I want to be a node in the network that is trying to verify a bunch of transactions, and I slip in a transaction that I should create 10 Bitcoin and give them to myself, people might not accept that. And so there are rules on who gets to create transactions and when they happen that we'll see later. So when they happen, they are sort of assigned new coin IDs. These are brand new coins with different values that are assigned IDs that can then be tracked through the system. Okay, so let's back up a little bit. Why are we not just verifying the signatures and accepting that as proof that a transaction is good? The reason is that verifying signatures doesn't prevent double spending, because that just verifies that the recipient actually received the money from someone. It doesn't verify that multiple people didn't receive that money, or that the spender is not spending the money multiple times. We need to see the whole set of transactions to sort of validate that this money wasn't double spent. And so validating the whole set of transactions can be expensive, so we're going to do it in this big network, the Bitcoin network. Okay. So this is where we come up with verifiers, also called miners. You've probably heard about Bitcoin miners. You can buy specialized hardware to do Bitcoin mining. It's really great to do Bitcoin mining where energy is cheap. For example, right next to a power plant, preferably in China, where you can get the power more cheaply. But it's basically going to be a lot of work to do a verification. So the goal, remember, the goal of verification is to prevent bad transactions from being verified. We want to make sure we're only verifying that if we verify something, it only incorporates good transactions. An evil verifier could accept a transaction that is invalid and say that it's valid, and if nobody looked, then people would accept that transaction, for example, double spending of something. So we want to make it difficult for evildoers to do this, and we're going to do that again by making it computationally difficult. By saying you have to do quadrillions of calculations, a single evildoer probably doesn't have enough computing power to pull that off. So what is a hard computation to do? Well, in this class, one of the things we've learned is that sort of breaking a hash function is very difficult. You kind of have to try to find a collision. You kind of have to try almost all possible combinations. So that, in effect, is the difficulty or sort of the challenge that is part of Bitcoin as computational work. So the puzzle you have to solve to verify a transaction is that you are given a block, the blockchain, the block you want to verify. It's going to have all these transactions, the previous hash, and it has this nonce at the beginning, which is a random number. And your job as a verifier is to figure out the value of the nonce, so that when you compute a SHA-256 hash, the target space at the front of the hash is all zeros. Right? So it's very hard to sort of make a hash produce special values. And so it means you basically have to keep trying lots and lots of nonces over and over again until you find enough target zeros. So if the transaction is hello, we're going to compute SHA-256 of hello colon 0. We'll see what it is. Oh, there's no zeros. Compute SHA-256 of hello colon 1. You look at it. Oh, there's no zeros. Eventually, we do SHA-256 of hello 917712, and we have 4 leading zeros. So this last one would be accepted as the winner if the rule was we needed 4 leading zeros. So this is basically a race. All the verifiers out there, all the miners, the nodes in Bitcoin, they are all madly computing hashes with different nonces, trying to be the first node on the network to find a nonce value that gives them a hash with the right number of zeros in front. And this is the essence of how we're going to verify Bitcoin, or how we're going to, the work that it takes to verify a block in Bitcoin. Any questions? Right? So we have some block of data. We need to find this little nonce we put in the front such that when we hash it, the leading zeros, the leading bits of that hash are going to be 0. Okay, so if there's 2 leading zeros, then we say 1 in 16th chance for each of them. So it's a 1 in 65536 expected trials. So the challenge is, suppose when Satoshi created Bitcoin back in 2008, he said we need 4 leading zeros, or 8 leading zeros, because that seems pretty hard. The challenge is that computers are getting faster every year, and so the time that it takes to actually find a hash that has leading zeros goes down every year. Furthermore, as you have more nodes in the network, you have more people looking for hashes, you might find the hashes very, very quickly. This might make it easier for someone to sort of subvert and create an alternate branch that has bogus transactions in it. And so there is a parameter to to this, which is the number of leading zeros is actually something that the protocol sets itself. And the idea is it should take about 10 minutes to find a hash with leading zeros. And if people find it too fast, then the system will start adding extra zeros to the front. And typically that happens every 2 weeks or so. Hashing gets fast enough that you have to find, and that it sort of slows down by saying you need an extra zero in front. So the time that it takes to verify a transaction is more or less constant at 10 minutes, even as the amount of power devoted to Bitcoin, the amount of processing power, goes up by a factor of 1 million or something like that. Because we can just, this is the nice thing, is we can make the problem arbitrarily hard by saying how many zeros we need. You know, ultimately you could say we need a hash that is all zeros, which would take, 2 to the 256 computations to figure out, which is way too many. Okay, so there's some properties that this is called a proof of work, that you basically have to do a lot of work and prove that you've done that work in order to find the hash. There are no shortcuts, hopefully with a good hash, to finding the answer. So the only way to do it is lots and lots of computation. So one nice property is that it is very difficult to compute. So in 2014, it took about 10 to the 20 hashes globally across all computers for each block. So this is more than the quadrillion I was talking about. And you can rest assured the number is much higher. So this is sort of a huge amount of work that it takes. And it means that any single computer probably can't do this many hashes in 10 minutes. So what this means also is that that it's very hard to sort of get ahead of the system. Suppose I am a rogue miner and I'm a rogue verifier and I want to verify bad transactions. I need to have enough computing power to find that special hash before anybody else. And it means if I have a minority of computing power, chances are good that the real valid nodes will find it instead. So this is sort of the probability of finding this is sort of the probability of finding the next hash, and it's sort of, for an individual miner, it's basically the time it will take you to find is 10 minutes divided by the fraction of hash power. So if you have 1/10 of the hash power, it should take you about 100 minutes on average to find a block. 1 in 10 times you get lucky and find it early. But a lot of the times it will take you much longer. So the goal here, as I said, is that on average across the entire blockchain network, we wanted to take 10 minutes to find the next hash. The second property this has that I mentioned is that the cost is parameterized. We can adjust the number of zeros and we can recalculate this so that as soon as hashes start being found too fast, we can add an extra zero to the edge to make it take twice as long. So we can have a continuous scale where hashing gets harder and harder. The third property that's nice is that it's very, very cheap to verify that an answer is correct. Because all you have to do is hash a block, look at the output of the hash with the nonce that somebody proposes, and see, does it have leading zeros? So in a sense, this makes it a one-way function. Because it's very easy to verify this, but it's very hard to guess what that nonce is. Or very hard to compute what that nonce is. It's not as hard as encryption because we don't have as many bits to guess, but it still is very computationally intense. So what this means is, why would somebody do mining, right? This is hugely power intensive to do these 10 to the 20 computations. So this means there has to be some reward. And it sort of says that you better hope that the reward of mining, which is, we'll see what they are, there's a reward for new Bitcoins plus fees. If the reward is greater than the cost of the hardware you have to buy and the electricity you have to buy, then you can make money doing mining. So if you control a botnet, then your hardware and electricity cost is zero because you're using somebody else's computers. So this means that if you can solve any of these puzzles and get the reward, you can make money using your botnet for doing mining. So it turns out there's quite a few botnets that do this. There's many Android applications that will do Bitcoin mining on your cell phone in the background, using up your battery to try to make their application owners money through Bitcoin mining. So if you have access to free computing cycles, it's a great thing. There's a lot of people who have been fired for running Bitcoin miners on their computers at work, trying to make a little money on the side. So I should get some permission. So these are sort of the aspects of how Bitcoin is decentralized. Who maintains the ledger? the ledger is not maintained by any one entity. It's distributed across this network by all agreeing on which block will be the next chain, will be the next in the chain. Who has authority over which transactions are valid? There is no entity that has authority, but whoever does the valid nodes that do verification will verify that the transactions in the block are valid, and they can be, that correctness of that can be checked by everybody else to see if they will accept a block. So the fact that you have to sort of get the whole network to agree on what the next block of transactions is does that verification for you. Who creates new Bitcoins? Well, the protocol, as we'll see in a little bit, creates new Bitcoins. Who determines how the rules of the systems change? So we haven't talked about this. The rules of the system are all embedded in the code. And so it means that if you can change the code, you can change how Bitcoin operates. So to some extent, you have to change the code and get a big enough fraction of those people running Bitcoin out there to change with you. So there are sort of lots of politics, and there's been some forks where people have taken Bitcoin and sort of split it and take some of the Bitcoin with one fork of the code, another bunch of Bitcoin with another fork of the code. And the final question is, how do Bitcoins acquire exchange value? Like, why is Bitcoin worth anything? Right? This so far is just a protocol for exchanging mythical numbers through encryption. Why would a Bitcoin be worth anything? And that is a lesson for an economics class, not for a computer security class. And I can't really answer that. Okay, so we're getting near the end. So once we have our miner has been computing away, found a hash function, they found the right value, nonce with the right leading zeros, they're going to announce it. So they'll broadcast it to the network. Everybody else, when they see this, will sort of see that the value works. They will stop trying to compute because it's already been found, they're not going to win, and they will start to work on the next entity. They can also verify that the block is valid so that they can sort of see all the transactions were legitimately formed in there. And so when you add a transaction, this is the stage at which your transaction has actually been accepted by Bitcoin and is real. So this means that if you want to pay me money, it's going to take about 10 minutes before that payment is accepted by the Bitcoin network and added into the blockchain that is globally agreed upon. So there's a question of, after 10 minutes, should you believe that your money has been delivered or not? Any thoughts? Are there still bad things that could happen? Yes?
Probably not. Somebody else might want to block another one after that, and they have the longest proof of work chain.
Right. So if you wait 10 minutes, it's possible that somebody else finds another proof of work hash very close in time, and that they actually get disseminated slightly faster, and that blockchain that said the block that said yours was accepted ends up not being accepted. And so what you really want to do is wait for some number of blocks afterwards, because remember, you want to be in the longest blockchain, the longest chain, and so you want to wait until it is long enough that you're satisfied yours can't be rolled back. To see what a malicious node can do, if we have this, see how the money was actually spent. So that's how we prevent a double spending attack. So this is sort of the what a merchant wants to do, which is wait until they're confident, and the probability of a double spending decreases exponentially, because with each subsequent block, some fraction of the network is working on the new chain, which means they're going to find an answer faster. The old chain, which doesn't have many people working on it, will likely take more than 10 minutes, maybe 15 minutes to be extended. And so as you wait more and more periods, more and more people go to the longer chain, and it gets further and further ahead because there's more people working on it. The other chain with fewer people working on it sort of doesn't get as extended as fast, and it becomes more and more clear which chain is longer. So as I said, there is no hard and fast guarantee this works, but in practice, if you have enough valid miners in the system, they will gravitate towards the same chain, and that chain will keep getting longer and longer, and any other fork will die off. Okay, so one thing to note is we are using totally random people on the internet to transfer money for us, and you might be a little suspicious about trusting random people in the network with millions of dollars of Bitcoin, right, to sort of do the right thing. So what this means is this kind of comes back to economics. How do we give people an incentive to do the right thing in this network? So far, everything is just a protocol. We haven't said why anybody would be a miner, and would contribute to this. And this assumption is problematic because you could think about miners might collude. You know, if you're double spending, they might want to do their own double spending by colluding and paying each other to sort of let money be spent twice and make a lot of money off of this. So we want to penalize the nodes that create bad blocks. That's difficult to penalize anybody because there's no money involved here necessarily. What we can do instead is we can reward the nodes that create the good blocks. So reward people for doing the right thing and don't reward them if they do the wrong thing. So the first incentive is that if you find the hash, then you get some Bitcoin out of that. So the creator of a block gets to create new Bitcoin in that block that is transferred to their public key. So this is the biggest incentive. If you find that hash, then when you create the chain, you're going to incorporate a transaction that says we're creating new Bitcoin and the new Bitcoins belong to me. And everybody agrees on this as being a valid transaction. So it used to be you got 25 Bitcoin initially, then it was half to 12.5 Bitcoin. I don't know what the current value is, but it's the same incentive. If you find that magic hash nonce value to make the hash work out, you get a bunch of Bitcoin out of that. And this is sort of the biggest incentive to actually do the mining because you get new Bitcoin. So as the value of Bitcoin goes up, your incentive to spend money on hardware and power goes up also. It turns out there is a finite supply of Bitcoin. There can never be more than 21 million Bitcoin in the system, which means that the value will sort of keep going up to some extent. Hopefully the idea is it'll keep going up because it is sort of a finite value that gets, the total is worth more and more. And this should last until about 2040 for people to keep mining and keep getting rewarded in Bitcoin. So that is one incentive to do this. What happens though when you run out of Bitcoin? Why would anybody keep running the protocol? So the second piece of how this can work is a transaction fee, right? So just the way that Visa and MasterCard charge sellers 2%, we can have a transaction fee inside Bitcoin. So how would this work? What it would do is it would say inside the transactions that we're going to verify, we are going to include some transaction fee that goes to the miner. So when we validate a block, the block will read in all these Bitcoin, pay people out, but it will subtract some fraction of that Bitcoin and give it to the miner instead. Now, because everything is signed by the person spending money, this has to be agreed upon. The person spending has to incorporate this, but miners can make it work by saying we're not going to validate transactions that don't incorporate transaction fees. So this allows you to sort of get directly paid when you validate a block. You can get paid for validating that block by keeping all the transaction fees inside the block, even if you don't get any new Bitcoin out of it. Does that make sense? I think so. Okay, so the biggest threat to Bitcoin is this notion of a 51% attacker. Suppose somebody controls 51% of the processing power working on Bitcoin. What are the things they can do? Can they steal your coins? And the answer is no, they cannot steal your coins. If you don't spend them, they can't take them away from you because they cannot reverse your public key and find out your secret key, which is how you spend things. So even if somebody controlled all the Bitcoin power, they couldn't take that away from you. Could they suppress some transactions? So they could by only sort of verifying blocks that don't have certain transactions in them. But they can't sort of suppress transactions from the whole network. They'll be visible to other people in the network. They just won't be incorporated into the blockchain because the 51% they control will sort of exclude those transactions. So it'll mean that certain transactions don't get processed. Could they change the block reward? And they can't do this because the reward is sort of agreed on by the protocol. It's not something that is set by the miners themselves. And so they can't enrich themselves too much. They still have to do the work, but they can sort of choose which transactions to incorporate. And it could hurt confidence in Bitcoin because you would know that a small fraction of people are sort of controlling this. So people work very hard to sort of make sure, try to make sure that there's enough different people doing mining that nobody controls the whole lot. So let's see, it is 10:43. I think I will not talk about Ethereum. You can read about it on the course reading if you're interested. But that is the essence of blockchain, and sort of how it works, how it gets monetized, why people are talking about it, why it's using some major fraction of the world's power supply. Any final questions? No. Okay. Oh, yes.
During the elongation of the blockchain,
Yeah.
the chain, so the chain, the node of chain is not necessary to do transactions and also be verification.
So each block in the blockchain is a set of transactions. And then the verification is really the finding that nonce that makes the hash value average to zero.
So if I can be Bitcoin and I didn't spend it, so my chain will not be elongated. So would that be a
Well, so when you get a Bitcoin, suppose Jane gives you a Bitcoin, there will be a transaction in the blockchain that shows Jane transferred it to you. So that will be in the blockchain. And then as long as you hold that Bitcoin, there will be nothing else in the blockchain. There'll be nothing else about that particular Bitcoin until you do something with it. But the transfer of the money to you will show up in the blockchain.
yeah, I mean, but I need to get, let me make the chain longer so that I could win the race.
You do that, the way you make the chain long, the way you make the blockchain longer is you're accepting transactions from other people participating in Bitcoin. You don't need to do it yourself. Everybody in the world spending Bitcoin submits transactions to be verified, and by verifying their transactions is how you make the blockchain longer. Here, signed by A, pay to B, with some hash. We could have another block that is signed by A that says pay to key A prime instead. So we now have two blocks in the system that have both been verified, and this is how a double spending attack is here, right? So there's no chain that is invalid. Both of these chains are perfectly valid. The difference is that they incorporate different transactions. And so we need to make sure that only one of these chains survives and that everybody agrees on it. And this is where agreeing on which is the longest valid branch helps. And so if we just wait a little while, we will see which is the chain that all the miners in the network agree on. So while these both are out here, all the miners in the network we're going to start choosing. And remember that one of the policies is pick which of the two proofs of work have more zeros in it, so they will sort of tend to pick towards one and very quickly start extending that chain. So if you wait another 10 or 20 minutes, you can see that one of these chains withered off, the other chain actually continues, and then you can sort of, for some other node, how do we decide which is the right answer? So there's sort of two ways to do this in Bitcoin. One is very simple. You look at the two answers, TX1 and TX2, and you count the number of zeros in the answer. So the answer is going to be a number. You count the number of zeros. Whichever one has more zeros is the one everybody who is a legal, well-behaving node will agree on. So node 5 and 6, which I assume are correct, can look at these two. They will all look at both, and they'll say, okay, we agree on TX2. It has more zeros in it. It doesn't mean that if there's badly behaving nodes, they have to accept this. Badly behaving nodes can still accept puzzle TX1. And this will all make a lot more sense when we go on.